Hello friends, myself Dr. Nagpuri, and right now I am at CSIR-National Chemical Laboratory, Pune. Today we have with us Honorable Dr. Sadhu Sir, scientist CSIR-NCL Pune, and Sir will going to talk on scanning tunneling microscopy, which is called STM technique. Basically, STM is a surface technique, and I request Sir to explain the principal applications and working of this instrument. Over to you, Sir.
Thank you, Dr. Nagpure, for your introduction. So, as Dr. Nagpure mentioned that, so I am going to explain the scanning tunneling microscopy, its working principle, electronics and application. So basically, scanning tunneling microscopy, it depends on the principle of quantum mechanical tunneling. So in quantum mechanically, if you have two surfaces and then it has a potential barrier, and the electron basically tunnel from one potential barrier to the next potential barrier. It's called as quantum mechanical tunneling. So basically, the scanning tunneling microscopy depends on this principle, quantum mechanical tunneling. So in STM we have a sharp tip, very sharp tip, atomically sharp tip, and that tip is made up from tungsten, platinum, iridium, or silver or cobalt, depends on the application. And then it's the tip like basically made using electrochemical etching. And once you have a tip and then you have like a sample, and then the distance between tip and the sample, it has to be 10 angstrom or 1 nanometer. So if you apply little bias in the potential between tip and the sample, and then the electron tunnel from sample to tip or tip to sample depends on the polarity of the bias. If your sample is positively biased, then the electron tunnel from tip to sample, and if your sample is negatively biased, then the electron tunnel from sample to tip. And then after that, the electronics, STM has electronics, is preamplifier. So the preamplifier is connected to the tip. Then we have the linear amplifier, then we have log amplifier, and then the lock-in amplifier. And then there is a data acquisition card between electronics and your computer interface. So this is the instrumentation for the scanning tunneling microscopy, and then we need to have vibration isolations. So there are two types of vibration isolation. One is acoustic vibration isolation, in the sense if somebody speaks, something is going nearby the instrument, then that generates vibration isolation that basically affects the electron tunneling, because that is electron level tunneling. So vibration like acoustic vibration also affects the electron tunneling. And then the acoustic like building vibrations and then some disturbance, these vibrations are in micron level. So that also affects in the electron tunneling. So that has to be like taken care during design the instrument, like acoustic vibration isolation and vibration isolation. And then the application of this instrument. So using this instrument you can study conducting and semiconducting samples. Your sample has to be atomically flat, like highly oriented pyrolytic graphite, silicon, single crystals of all noble metals like palladium 111, gold 111, like silicon 111. These materials can be studied using scanning tunneling microscopy. If you grow some samples on the surface, like if I can say supramolecule, like organic molecule, if you put the organic molecule on cobalt 111 surface, you can find the band gap of that molecule or homologo gap of the molecule or density of states of that molecule using scanning tunneling microscopy. And in single crystals also, in HPG also, you can find the density of state of the molecule, because density of state basically in STM study you can study the spectroscopy part, that is called as scanning tunneling spectroscopy. You need to apply the bias and pick up the current from the preamplifier. So that is if you like scan from negative to positive bias, your current varies from like positive region to the negative region, and if you take the differentiation of that current IUV graph, then that will give you the density of state of that material. And in that graph you can find the band gap of the material also if your sample is semiconducting.
Yeah. So suppose if you have a catalyst, say for example, we have used a gold metal and we deposited the gold nanoparticles on the carbon surface. So can we able to investigate the surface interaction between gold particles and the carbon by using STM technique?
Yes. So that is actually again very good question, in the sense, if you have gold particle on the carbon surface, or if you have any nanoparticle on the carbon surface, metallic nanoparticle. So what happens if you apply the bias, the electron tunnel from the carbon surface to your nanoparticle and from nanoparticle to your tip. So that will reflect in the iris spectroscopy.
Oh.
So that is called double barrier tunneling junction, called as double barrier tunneling junction. So if you, from that you can find how much time required to tunnel electron from carbon surface to the nanoparticle and from nanoparticle to the tip.
Yeah. So now for instance, suppose I am now having two catalysts. One is having carbon supported gold catalyst, and one is having nitrogen doped carbon supported gold catalyst. So will it be the STM graph will be different in both the cases, or will be same?
Yes. So in both the cases you will get, if you like did differential mapping on those surfaces, then you will clearly see the nitrogen doping and without nitrogen doping, how the surface electronic structure looks like. So that's the beauty of that instrument. Secondly, if you pick up the tunneling current with a time, that is called noise spectroscopy. From the noise, you can actually measure the tunneling current fluctuations. So we also worked on this instrument during my PhD actually.
Yeah, so see guys, so STM technique is one of the promising technique we have in, if you wanted to understand the chemical and physical aspects of the material or for any catalyst you are using for your catalysis purpose. Thanks for watching. I again thank you very much, Dr. Sadhu sir. Signing off. Thank you very much.